learn one important thing about physical systems or about any such systems, which is time averaging and and now I will also use over here ensemble averaging. When I say ensemble averaging, I mean if you want to actually find an average quantity anywhere, what you would do is that look at all possible configurations of the system and then see how many of the given kind that you're looking for occur in all those possibilities. So if you have a die with faces marked and you throw a die, you know that there are 6 possibilities of a particular number coming up on top. Six numbers that can come on top. And if you want to find the probability of any one of them, you will roll it again and again, and you over a large number of time, and you will count the number of time 1 occurs, or 2 occurs, or 3 occurs, or 4 occurs, or 5 occurs, etc. And you will eventually come to conclude, if the die is quite correct die, then you will come to conclude that all of them occur with a probability equal to 1 over 6. That P1 1 over 6 because there is equal probability of each one of these things, because the die is supposed to be a very nicely made die. There is no hanky-panky in it. Okay? So this is done in 2 different ways. This number will be found, this number probability is always given as number of times a particular event occurs divided by total number of events. That is the definition, standard definition of probability, and you have learnt it. I think you did this in your O levels or matriculation. And therefore, if you want to really find this number, what you have to do is to go to a very, very large number. And of this, this happens when you go take limit n going to infinity. Very, very large number. And only then you would be very certain about this number. So you can achieve this in 2 different ways. And these 2 different ways are that you can take this die and make a large number of copies of this die. You take, say, 100 dice, and you throw them all at one given time. There's something going on over there? Please pay attention. Okay? If there's any problem, I can see that the people on the 2 sides of you are getting distracted. So if you have something else on your mind, I can open the door for you to go out. Or listen to me. So the number has to be very large and has to go to infinity for you to get a correct value of the probability of an event. So you can do it in 2 different ways. You can take a very large number of dice and throw them all at once, and then count how many times a particular event has occurred on top, and calculate this number, and you will get this number, depending upon how large your system was. There is this possibility, and that is the possibility of ensemble averaging. Because what you did was you created a large number of copies of the same system. You created an assembly of these particles, created an ensemble, and of this ensemble you found out the averages. How many times A occurred, how many times B occurred, and so on and so forth. A second possibility is to take just one die and throw it 1,000,000 times, 100 times, 1,000 times, a large number of times. So that will be actually time averaging. You take one system and do it a large number of times and then see how many times a particular event occurs. So there is this therefore time averaging and there is ensemble averaging, and there is a very basic hypothesis which is called ergodic hypothesis. Name is very fancy, you must agree. Ergodic hypothesis actually says that both of them will give you the same result. The result will not be different. Which means that if you really, you can avoid taking time averages, and you can do an ensemble averaging. And this is why we are worried about, and this is what statistical mechanics always worries about, creating ensemble of the system. Okay, and we will come to this particular ensemble averaging later on also. But then here we are doing a time differentiation of H, and as I said, thermodynamic quantities so far in thermodynamics we did not consider time as a variable, but time has entered because you have taken averaged out quantities, and time has entered into this because of this hypothesis in which we said that all these large scale quantities were measured either statistically, either through an ensemble averaging or through time averaging. Okay, coming back now to the Boltzmann-H theorem. The H theorem says that this should be time evolution should give of H should be a negative quantity. H should decrease with time. H should decrease with time. And we started to derive this, and I'll repeat some of these steps that I had done. How would you look at this? You see, dH by dt, as we derived last time, is simply sum over I dpi by dt times log pi plus 1. We derived this last time. And we stopped to think of ways to calculate dpi by dt. How do probabilities change with time? Probability is this is the probability of the system being found in the ith state. The system can be found in a large number of states, and the probability pi of finding system in an ith state, it depends upon time, and you want to find out how does it depend upon time, or how does the time variation take place. And this is where the exercise that not the exercise, but the in the derivation yesterday, in the last lecture, I introduced a transition probability. This is the probability of transition from one state to the other. I called it pi ij. It is the probability of a particle making a transition from state I to state j. Okay? And we said that this change in dpi by dt takes place due to transitions among states. The states we have in mind are microscopic states. Somebody else's mobile is also on. Please switch it off. So this change, time change in pi occurs due to transitions among states. And transitions in the sense that if this is the state I with dot, I think, okay, this is the state I and this is the state J or K or many other states, then the probability of finding the particle in state I or system in state I will change in time because of particle itself going from state I to any other state, or because of particles already present in other states making a transition to state I, making a changeover into state I. So there is this two-way exchange that takes place that we call transition, and there is this probability Pi, with this probability Pij. So if we want to look at, to find dPi, time rate of change of Pi, we say that this will be equal to the probability of particle which are particles which are all in different other states making a transition into ith state minus the probability of particles already present in the ith state going out of the ith state. So this will be equal to, as I wrote last time, particles making a transition from all the jth state into ith state. So there are particles in the j states, each one with the probability pj, and pj is equal to 1 means that particles are there, 0 means the particles are not there. So when they are there, they make a transition to the ith state with this probability, and this is happening from all other possible states. And then there is a transition from jth state, from the ith state to jth state. So particles go from ith state to jth state, and the particle will have to be initially present in the ith state, and some will have to be over all the j states, because it will have to be from ith state to any of the jth states, to all the jth states. So therefore we have here, and this will be depletion of particles in the ith state, and this will show the increase of particles in the ith state. Haji? Did I make a mistake? Kya hua? I'm sorry? Oh, J जो है वो मैंने I बना दिया, I की तरह लिखा है. अच्छा वो कौन सा J है? All right. अगर इस तरह कर्ल किया हुआ हो तो ठीक है, हैं? Okay, I should have been a calligrapher, you know. ये आपको लग रहा है कि ये J नहीं है? Is that the? ये वाला, ये J नहीं है. अरे भाई मुझे तो आप लोगों ने बहुत परेशान कर दिया.
सर ये समेशन कीजिए आए या जी?
अच्छा, ये समेशन किसके ऊपर होगी ये सवाल है. समेशन किस पे होगी ये सवाल है. ओके, देखिए हम आई पे समेशन तो नहीं कर सकते क्योंकि यहाँ पे पी आई है. आपको एक बेसिक उसूल मैथमेटिक्स का ये पता होगा कि जब किसी वेरिएबल के ऊपर आप समेशन कर देते हैं तो सम्ड क्वांटिटी फिर उस वेरिएबल के ऊपर डिपेंड नहीं करती, उस इंडेक्स पे डिपेंड नहीं करती. ठीक है ना? वरना फिर सारी अगर यहाँ पे मैं आई पे समेशन कर दूंगा तो फिर उसके बाद उसका मतलब ये हुआ कि तमाम आई की मैंने प्रॉपर्टीज देख ली, लिहाजा वो आई एथ जिसको मैं देखना चाहता हूँ वो मैं देख नहीं पाऊंगा. ऑलराइट, दिस इज वन वेरी बेसिक thing about mathematics from mathematics. So it will have to be summation over j. एक तो पहली बात ये थी, मगर दूसरी बात जो है वो फिजिक्स के लिहाज से, I think what you asked was from the point of view of physics, कि जो transitions हो रही हैं उसके मुताबिक. पहली term, the first term tells you all the particles which are leaving their own states and coming into the ith state, so that the population of the ith state increases with time. We want to see this change in population of the ith state in time. This will depend upon particles coming in from other states into the ith state, and then particles which are leaving ith state and going into all other states. So this is the one where particles are actually coming in from all other states into the ith state. All other states into the ith state, and therefore we are summing over J. And here particles are leaving the ith state and going to all other states, or any of the other states. And that we write by again summing over J. The difference is that in this case you must make sure that particles which we say is coming in from the jth state already existed there. It had a probability Pj, so that it could come to ith state. And here we must make sure that there was a particle in the ith state so that it could go to the jth state. All right? So that is why we wrote Pi over here. Okay? So this is perfectly fine. I think there is no problem with this.
So the first one is Pj.
ये summation? That was the J that worried people, eh? Yes, this is Pj. Okay, I should now make it a point to write P like a professional calligrapher. Okay? So is that okay now?
Yes.
This is the J. This is J appearing here, and in these places. Okay, so I'll be careful, and this will be equal to, we can easily see, we also note that P, we can assume that the transition probability will not be biased. It will be the same going from ith state to jth state or jth state to ith state. It will not be biased.
Transition probability की dimensions per unit time.
Transition probability, normally probability is taken as a dimensionless parameter.
So लेकिन वो दोनों sides equal करने के लिए ना, क्योंकि left side पे per unit time.
Oh, that is not, that dimension does not go into probability itself. Oh, you are saying transition probability की क्या होगी?
Yes,
Okay. Transition probability जो है, that is with per unit time. Okay, you are right. Transition this probability is without any dimension, but this probability will be with time. Yes, per unit time.
So could you explain why is the transition probability same from I to J and J to N?
Because particles are essentially in a gas exchanging their states.
So जो आपने इस डायग्राम में ये चार डॉट्स बाद में शो किए, चारों के चारों J नहीं रिप्रेजेंट करते?
Yes.
So तो एक पार्टिकल
No, चारों के चारों J का मतलब ये हुआ कि J then is defines a state which is other than I. So all the other states we are calling them J.
Other states से I में आने की probability कम नहीं होगी as compared to I दूसरे state?
No, there will not be any difference in the. इनका सवाल जो है वो ये है कि wouldn't the probability of any problem होते हैं? कोई मसला है ना? नहीं. कुछ okay. जो सवाल इनका है वो ये है कि wouldn't the probability of all the particles coming in from the other sides into I be less than the probability of particle going from side I to all the other sides? Greater than, if not less than, or unequal. There should not be any such reason. There can't be any reason why this should be different, because particles are continuously changing their states. Think of I and J in terms of classical states. Classical states are basically given by their positions. Okay? X, Y, Z define the position of a particle. And if particles in a gas are continuously changing their positions, this one flying out to this point and this one is flying out to this point, and this one is flying out to this point, then why should there be any difference in this flying to this place and this flying to this place? This is all the same, right? So the probabilities are the same. Going from one state to another will be the same. Okay? And because of this now over here, what we have is, it is summation over j pi, and I can write it as pi ij and then pj minus 1 minus pi. All right. So time evolution of pi will be equal to this thing under this supposition. Fine. Now what we do is go back and substitute this in this expression here. So dH by dt will be equal to summation over I, and now I put for dpi by dt that expression summation over j. कोई बोल रहा है, कोई बात कर रहा है, इस वक्त आवाज आ रही है मुझे. किसकी आवाज आ रही है? If there is a question, please raise your arm. I will answer your question. आपकी बातों से दूसरे लोग डिस्टर्ब हो रहे होंगे, ठीक है ना? Summation over I and j, and this will be, I can now put in that quantity pi I j and pj minus pi times log pi minus 1. Now we will do a trick. क्या हुआ? Plus है, sorry, plus है. Yep. Now we will do a trick, and you will say that look, we had taken dpi by dt, and we could have easily, suppose we had started with I can make a very straightforward argument also. I and j are completely arbitrary, so I could interchange I and j. I could say, make it this statement over here. And if I make an interchange of I and j, it would be summation over I and j again. Pi ji pi minus pj times log pj plus 1. So this I could only say that look, I and j are completely arbitrary. I could have started with rather than dpi by dt, or I could have taken summation over j initially and then calculated dpj by dt, and would have ended up with an expression like this. All right. So if this is equal to this, then I can easily subtract that from this, or add them, subtract them from each other, and I would I can actually sum them up and end up by saying that dH by dt is equal to, apart from a factor of half or whatever, summation over I and summation over j, pi, I have to be careful with j, pi ij times pi minus pj times log pi. What do I have over here? Log pi minus log pj. If I do log pi minus log pj, then I will have to put a negative sign over here. So log pj, I will put a negative sign over here and make it log Pi minus log Pj. Okay? Making use of the fact that this is Pi minus Pj, this is Pj minus Pi. And therefore I can write them together in this particular form. Maybe I'll put a, when I subtract them, it will be just this. Sorry? Okay, what I did was I said that this expression is equal to this expression. And I added this into this, I got this. Okay? Is that difficult to see? This is pretty simple. I have this expression, so first you will have to agree with me that this is the same as this. And if you agree with me that this is the same as this, then I simply added them up, because each one of them is equal to dH by dt. I added them up. So there will be a factor of half, you're saying. Huh? So, okay. So I will say that this is equal to minus 1 over 2. Okay? Will that be good? Okay. So this is the expression. And here it is very, very clear that if Pi is greater than Pj, then this is positive and this is also positive. No, and therefore the whole quantity is negative. Okay? And if this is negative, this is also negative. And again the whole quantity is positive. The point is that this product for whatever value of P and J is always a positive quantity or a zero quantity. This is always a positive quantity. And therefore you have shown therefore that d by this is a negative quantity. Okay? तो आपको यकीन नहीं आया? It's clear here? Huh? Good. And because of this, actually one can, dH by dt will be equal to 0. Somebody had asked initially, what if dH by dt is 0? This will be 0 if Pi is equal to Pj. Yeah. So how did I get a negative here? When I added them up, there was this Pj minus Pi, Pi minus Pj, right? So there was the minus sign to come with either this or this. Okay? And that minus sign is over here. So you will see it easily. This is dH by dt will be equal to 0 if Pi is equal to Pj. Alright? And otherwise dH by dt is a negative quantity, and we relate this then to our function entropy. We had said that entropy is equal to minus k summation over I Pi log Pi. Therefore we are saying that S equal to minus k times H and therefore we also show that although what it shows is that d by dt of H is a positive quantity.
So S is entropy?
S is entropy. I wrote over here for entropy with a constant K, the Boltzmann constant. So entropy and Boltzmann's H function are related to each other. This actually goes into making this conceptual foundation of the whole discipline of statistical mechanics and thermodynamics. When you say that various things that were being proposed at that time, the way they are all related. So entropy comes out to be related to H, and that is what this shows. And then we know that in our current discussion, we say this amounts to saying that delta S is greater than 0 or increases in spontaneous processes. That is a different statement. This is a different statement. Okay?
So you said that Pi minus Pj, that quantity is positive.
Right.
That term, the two terms are positive. So doesn't it contradict our previous assumption that, or the statement that the transition probability I from I to j is equals to j to I?
Oh, why would that do that? इनका सवाल जो है वो ये है कि आपने कहा कि ये चीज़ें जो हैं ये पॉजिटिव है, ठीक है ना? तो क्या इससे ये मालूम होता है कि ये हमारा assumption कि pi I j is equal to pi j I is false? I don't see why it should have any effect on that.
Because the probability, that term is only positive if Pi is greater than Pj.
Yes? No. This is not true. I said this is positive in whether Pi is greater than Pj or Pi is less than Pj. क्योंकि इसके साथ मल्टीप्लिकेशन इस टर्म की है. अगर ये पॉजिटिव है, अगर Pi पॉजिटिव है, Pi is greater than Pj, ये पॉजिटिव है तो ये भी पॉजिटिव है. अगर ये नेगेटिव है, Pi is less than Pj, तो ये भी नेगेटिव है. तो इस वजह से ये हर केस में पॉजिटिव क्वांटिटी है. And that is why we said that this negative sign that we took out earlier determines that this is going to be negative quantity.
So when entropy change is 0, it means that probability of finding a particle in ith state and jth state is equal.
So the question that he's asking is, if suppose we say that entropy change is 0, does it amount to saying that the probability of finding the particle in state I and state j is the same? ये सवाल है ना आपका? हाँ? We have only related, as far as this entropy is concerned, it is summed over all of these quantities. So it doesn't depend upon the individual probabilities at a given time. It is summed over all the probabilities. That is very important over here. It is summed over all the probabilities. In fact, अगर चाहें आप तो आप इसको यूँ भी लिख सकते हैं. If you permit me, I can write S as minus k times log p average. और एवरेज के लिए ऊपर बार लगाते हैं ना बाज़ औक़ात, तो एवरेज. क्योंकि एवरेज आपको लिखनी हो किसी क्वांटिटी की तो आप उसको तमाम प्रोबेबिलिटीज़ के साथ मल्टीप्लाई करके सबके ऊपर सम करते हैं. तो ये जो एक्सप्रेशन है ये वाला, ये एक्चुअली एवरेज का एक्सप्रेशन है.
So, but from the X theorem we saw that dh over dt is equal to 0 only if Pi equals Pj. Right?
Okay?
So ds over dt is also equal to 0 only if Pi equals Pj.
If you're saying if it is ds by dt equal to 0 in that sense, okay, with time it will not change if Pi is equal to Pj. लेकिन इसमें एक छोटा सा फर्क है, वो यही है कि यहाँ पे आप इनको ज़ीरो ले रहे हैं, इनको कहते हैं कि अगर ये ज़ीरो हो तो डेफिनेटली ये ज़ीरो होंगे. जो एक्चुअल थ्योरम का स्टेटमेंट है वो तो ये है कि इट इंक्रीजेज विद टाइम, बिकॉज इंडिविजुअली किसी पार्टिकल की प्रोबेबिलिटीज़ कैसी होती हैं. यू हैव 10 to the power 23 particles. You can, and you have 10 to the power I know how many a number of possible states of the system, right? And factorial number of states at least. N factorial, n is equal to the power 23. So you can imagine कि क्या magnitude है total number of possible states का. उसकी हर एक की probability के ऊपर आप s के ऊपर कोई judgment दें, this cannot happen, right? This is an averaged quantity, and therefore this is what I said, that this is an averaged quantity because it says that this is average of log p, proportional to average of log p. आपका सवाल था, आपका हाथ खड़ा हुआ था.
Maybe a similar question. If
Okay.
the transition probability of I and J are the same, And shouldn't the actual probability defined be the same?
No. इनका सवाल जो है वो ये है कि अगर ट्रांजिशन प्रोबेबिलिटीज की इक्वलिटी हो I से J जाने में और J से I जाने में, तो उससे PI और PJ को भी बराबर नहीं होना चाहिए, ये सवाल है। नहीं, ये ट्रांजिशन प्रोबेबिलिटी एक और चीज़ है और पार्टिकल का किसी स्टेट में होने की प्रोबेबिलिटी जो है वो कोई और चीज़ है। You can't talk of them at the same footing. कोई और सवाल? All right. So the accomplishment so far is that we have seen just another phase of this discussion, where we have related entropy to the Boltzmann H function, and have shown that entropy can be. One other point that I think there are 2 points that I wanted to make before I go on to. Let me take just one more point from the last discussion, which is interesting. We are going pretty slowly so that you have enough time to look at all possible aspects of the entropy function, and you can think about it and ask questions and do problems and so on and so forth. The point that I'm trying to make is that last time I showed that if you start with the S equal to minus K sum over I Pi log Pi, then from there you can actually deduce S equal to K log omega. All right, let me go back and remind you what these terms are. This is the expression that we have already seen. P's are the probabilities of microstates of the system, microscopic states of the system, and here omega is the total number of microscopic states. Okay, so here summation over I is over micro states of the system. Microstates means systems which are different in microscopic details, in which particles may have interchanged their positions, they may have gone into different energy states, and so on and so forth. So microscopic states are different. This is total number of microscopic states. Microstates is equal to omega. And in the last lecture, I showed a connection. I showed how one can go from here to here. Okay? And you must have already seen that. Today, I will take you from here back to that particular point. Starting from S equal to K log omega, we go back and derive S equal to minus K sum over I Pi log Pi. Why? Why do we do that? Isn't it convincing enough that these two are equivalent definitions of entropy? It is convincing enough that these two are equivalent definitions of entropy. But we want to look at this because that may tell us a little bit about how these calculations are done, and a little bit of flavor of statistical mechanical calculations. Not quite rigorous statistical mechanical calculation, but maybe a little bit. So I'll do that. Omega is total number of, we go from here to here, total number of microstates. And what is the total number of microstates? Omega is total number of ways in one, let me put it this way, in one sense, it is total number of ways of picking, no, total number of possible states, total number of, let me put this suitable word, total number of possible states chosen for n objects. So what is this? This is a particular way of looking at things. Total number of possible ways for choosing, total number of possible ways of choosing n objects, total क्या इसका मतलब होता है इसका? This is usually called Ni distribution. Ni distribution का मतलब जो है वो ये है कि आप कहते हैं कि पहली बात तो ये आपको ये एक छोटा सा मैं कॉम्बिनेटोरियस का जो एक्सप्रेशन है वो मैं लिख दूं कि इफ यू वांट टू फाइंड नंबर ऑफ वेज of picking or choosing A objects out of B, total of B objects, is simply how you write it as BA, which is defined as B factorial over A factorial times B minus A factorial. Okay? This is the standard relationship. क्या हुआ? ओह रेसिडुअल बाहर है, बिल्कुल ठीक है, सही बात है. And we use this to calculate omega. And omega would be by saying that there are total n objects with us, and out of these we first choose n1 objects. So there are so many ways of doing this, so many ways of choosing n1 objects out of capital N, and then we are left with n minus n1 objects, and then we choose n2 objects out of them. And then we are left with n minus n1 minus n2, and out of these we try and choose the number of ways of choosing n3 objects is equal to this, and so on and so forth. And mathematically you will put them in this particular form. So you will have therefore omega equal to n factorial over n1 factorial n minus n1 factorial multiplied by n minus n1 factorial divided by n2 factorial n minus n1 minus n2 factorial, and then multiplied by n minus n1 minus n2 factorial divided by n3 factorial and n minus n1 minus n2 minus n3 factorial, and so on. And these terms will cancel out, and you will be left with n factorial divided by n1 factorial, n2 factorial, n3 factorial multiplied by, and so on, which you can write as n factorial, capital N factorial divided by sum over, no, not sum, this is product. Product over I, Ni factorial. Product of factorials. Okay? So total number of microstates in the system is the total number of ways, total number of combinations you can make out of the total system. हाँ हाँ जरा करके देखें. हाँ हाँ आखिर में 1 बचेगा ना नीचे. जीरो फैक्टोरियल भी 1 ही होता है. All right. So log omega is equal to log n factorial minus log of product is sum of logs. So I will first write it as log of product over I Ni factorial, and then I will write it as log n factorial minus sum over I log of Ni factorial. Okay? And this we will need to solve, and we will use what is called Stirling approximation. Stirling approximation can be used only when the number is very large. For large n, log of n factorial is approximately n times log of n minus n only. Okay? And therefore, our log of omega is equal to n log n minus n, then minus summation over I, and inside I have Ni log Ni minus Ni. And I will put this, as somebody is correctly pointing out, I can say this is roughly equal to. Okay? And that is where we also notice that since sum over I Ni is equal to capital N, when you sum over all the particles occupying different states, you sum them up, this will be equal to total number n. Therefore, minus n and plus n will cancel out. So these two terms will cancel out. Minus n and plus n. And because they cancel out, we are left with n log n minus summation over I Ni log Ni. All right? We will need to do a little bit more of this algebra. We know that we can use this expression over here. We can use this expression over here by saying that I can write for this n summation over I Ni for this n, and then write log n minus summation over I Ni log Ni. Okay? I can actually then over here take this to this equal to sum over I n I, and inside the bracket log capital N minus log Ni. All right? I can do that, right? And this I can actually then write as, where is this minus sign? Okay, I will keep this as it is. This will be sum over I. Any problem? कहीं गलत कर दिया मैंने कुछ? नहीं, मुझे बड़ी आवाजें आई थी एहतिजाज की. बिल्कुल इस वजह से कि लॉग कैपिटल एन जो है वो एक कांस्टेंट क्वांटिटी है, आई के ऊपर डिपेंड नहीं करता, तो समेशन के अंदर उसको ला सकते हैं, कोई फर्क नहीं पड़ेगा ना उससे. ठीक है ना? तो समेशन ओवर आई एन आई, एंड आई कैन राइट दिस एज log of capital N over Ni. ठीक, क्योंकि log of quotient is difference of logs, which I can write as minus summation over I Ni log Ni over capital N. ठीक है, समझ में आ गया? समझा दिया? गुड गुड. पड़ोसी ऐसे ही काम के लिए होने चाहिए. गुड, मगर ज्यादा गपशप के लिए नहीं होने चाहिए. ओके, एंड नाउ आई कैन से दैट दिस इज इक्वल टू माइनस n टाइम्स समेशन ओवर I Ni ओवर n log Ni over n. So what I have over here is Ni over n, and I think I had perhaps said it somewhere. If not, then I can say it over here. Pi is equal to Ni over n. Number of times a state, the ith state occurs divided by total number of possible states, is the probability of finding particle in the ith state, probability of the ith state. If this is the case, then we are looking at log omega. Log omega is equal to minus n times sum over I pi log pi. तो ये हमने कहा था कि ये दोनों का रिलेशनशिप जो है वो हम वर्कआउट करेंगे. इसके अंदर ये n का फैक्टर एक है, which will be an additional factor which is basically added something which doesn't really make it very different, सिवाय इसके कि आप एंट्रोपी पर पार्टिकल निकालते हैं या एंट्रोपी पूरे सिस्टम की वर्कआउट करते हैं. ये एक ऑब्जेक्टिव था आज की एक्सरसाइज का कि आपको ये जो कैलकुलेशन जो मैंने की है यहाँ पे, ये कैलकुलेशन जो मैंने यहाँ पे की हैं, ये एक्चुअली स्टैटिस्टिकल मैकेनिक्स की कैलकुलेशन है. इसके अंदर आपने सिस्टम की प्रोबेबिलिटीज कैलकुलेट की हैं, आपने ओमेगा कैलकुलेट किया है, और आपने ओमेगा कैलकुलेट किया है बाय लुकिंग एट द टोटल नंबर ऑफ पॉसिबल स्टेट्स दैट यू कैन मेक फॉर द होल सिस्टम. You have done that calculation, the total number of possible states the system can have, omega, and that number, from there you did this calculation and ended up with the same result. All right. No big deal, except that you got a flavor of how these calculations are done. Next, I would also mention that क्या हो गया? कोई चीज समझ में नहीं आ रही. हेलो, कुछ समझ में नहीं आ रहा आपको? क्या चीज समझ में नहीं आ रही? अब तो ढूंढना पड़ेगा कि क्या समझ में नहीं आ रहा.
प्रोबेबिलिटी के अंदर आपने बीच में ट्रांजिस्टर प्रोबेबिलिटी डाल दी पाए वो स्टेप्स
वो तो बहुत पुरानी बात हो गई. चलें, ओके. अगर आपको वो परेशान कर रही है इस वक्त, वो आपको आइंदा परेशान करती रहेगी. सो वैसे तो उस वक्त पूछ लेती तो अच्छा था, बट आई कैन स्टिल गो बैक टू इट. और why don't you ask this question after the lecture is over? Okay, I'll explain this to you. Anything else? कोई हाथ खड़ा कर रहा था पीछे? नहीं, जमाई ले रहे थे हैं. ओह, परेशान कर दिया बेचारे को. Okay, and next, a very important thing about probabilities energy and temperature. If temperature of the system is specified, this is what I am going to write over here. If temperature of the system is specified, and system is known to exist in a number of different possible states, then probability of finding the system probability of finding the system in any one of these states, let's say rth state, is given by, and I'm giving you something without proving it, just writing it so that you know how this thing is calculated. This is PR, probability of finding the system in the rth state, as being proportional to, not equal to, proportional to exponential of minus ER over KT. ER is the energy of the rth state, and K is the Boltzmann constant, T is the temperature. And the whole factor, exponential of minus E over KT, is called Boltzmann factor. It is called Boltzmann factor. Boltzmann factor defines the entropy of, defines the probability of a state with energy ER. Okay? If you are asked what is the probability of finding the system in a state of energy ER at temperature T, you will simply write this. That will be good. And this proportionality will have to be removed, and this proportionality is removed by demanding, like all probability functions, that sum of all probabilities must add up to 1. Okay? Sum of all probabilities must add up to 1. If you demand that, then what you are saying is that sum over R exponential of minus E R over KT is equal to 1 times C. Sorry, I will put this proportionality constant and I will say P R is equal to some C times exponential of minus E R over KT, and therefore this is equal to C times this is equal to 1, and therefore C is equal to 1 over summation over R exponential of minus ER over KT, and therefore PR happens to be becomes exponential of ER over KT divided by summation over R exponential of minus ER over KT. Okay? And we should know that these exponential factors do not cancel out each other because we are summing over them. The only problem is over here, जो मैंने यहाँ पे एक छोटी सी गलती की है जिसका थोड़ी देर पहले मैंने बताया था आप लोगों को, जिसकी करेक्शन मुझे यहाँ करनी चाहिए, वो ये है कि मैंने यहाँ पे कहीं बात करते हुए ये कहा था कि जिस चीज़ को आप सम कर दें तो उसको लेफ्ट हैंड साइड के इंडेक्स में नहीं आना चाहिए, तो समेशन ओवर आई यहाँ नहीं हो सकता था. मैं अभी कुछ एक्सप्लेन कर रहा था ना ये यहाँ. So it can't have summation. If there is an index I over here, there shouldn't be any summation over I over here. Similarly, because J is being summed, so J should not appear over here. वहाँ पे मैंने ये नहीं है एहतियात की, जहाँ पे मैंने सम ओवर R वैसे का वैसे रखा हुआ जो गलत है. एक्चुअली मुझे यहाँ पे ये करना चाहिए था कि I would have said कि this is for state S. So, okay, S will may lead to confusion. State I, okay, so state I is equal to this, and therefore I would have said here that that is any index I, and hence over here I would not have that particular problem. Okay? So the probability is still proportional to this. This is a summed quantity over all of them, and therefore that should not make much difference. We have talked. This is the expression for. And my emphasis is when temperature of the system is specified. And let me take you back to my very first lecture. Temperature of a system is specified only when you connect it to a heat bath of that temperature. A heat bath actually specifies temperature of the system. So you have connected your system to a heat bath, and the temperature of the heat bath and the system come into equilibrium with each other. When they come into equilibrium with each other, they both have the same temperature. System will have the same temperature as the temperature of the heat bath. Heat bath by definition is such that even if it gives out some small amount of heat or takes some small amount of heat, its temperature doesn't change appreciably. Okay? So this is the situation when the system is in contact with a heat bath, and the system has come into equilibrium with the heat bath. And that leads us to actually describing closed and open systems. In the last couple of minutes, 3 minutes. Closed systems are completely isolated systems. We have often talked about them. All right? We don't need any further emphasis on that. Closed systems. Open systems can be open in two different ways. Open to heat transfer, heat or energy transfer, Heat is energy, right? So heat transfer is energy transfer. I need not have written that. Or open to material transfer, matter transfer. Now, in the first case, system being open to heat transfer is something which we have discussed several times during the last 9-10 lectures. We have said that you define a heat bath as a large source of energy, and you take and you put your system in contact with the heat bath. When you do this, the heat bath by definition is a very large source of energy, and it has a particular temperature T, and if there is a difference of temperature between heat bath and the system, there is a difference of temperature, the heat will flow from system to heat bath and so on. Why would it flow? It will flow so that both of them come to the same temperature. We just discussed this a minute ago also. Similarly, there can be a flow of matter. Some people call it open to diffusion of particles. The system, you can connect the system to a matter reservoir, a particle reservoir, a reservoir of matter. And there would be something which will determine whether there should be a transfer of matter from system to the reservoir or not. And that thing happens to be, in this case, temperature difference causes heat flow. In this case, chemical potential difference. So chemical potential is something that we have not defined yet. We will need to define it. Chemical potential difference causes matter to be exchanged. So if we bring two systems together, and I will call them, it is a system and there is a heat bath, large system. It is at chemical potential mu. Chemical potential is often written by the letter mu. Chemical potential of the system is mu s, and chemical potential of the reservoir is mu r. And if mu s is less than mu r, then matter will flow from the reservoir to mu s until such time. And what will be the reason for this flow? The reason for the flow would be to bring them to equality, to rise, to let the mu s, the value of mu s rise, so that mu s becomes equal to mu r. Okay, so that mu s becomes equal to mu r, and the system then, as when mu s and mu r are equal, particles will stop flowing from r to s. Vice versa, if mu s is larger than mu r, then a particle will flow from mu s to mu r until mu s comes down to the level of mu r, and then the particle flow will stop. So there are two drivers of flow in thermodynamics. For heat flow, the driver is temperature difference. For particle flow, the driver is the chemical potential difference. Please stop over here. Thank you.